Hey guys, welcome to our video for section 7.2, Math 112. We're going to be talking about verifying identities. So we've already talked about a couple identities in previous sections, right? In the last section, we talked about that Pythagorean identity, right? And for those of you that have already forgotten, right, that was our lovely sine squared theta plus cosine squared theta equals 1. And so that was an identity, and we kind of talked about how we got that, where that comes from, and it comes from the unit circle. The fact that sine theta is equal to y, and cosine theta is equal to x. And so using the unit circle, right, and that's where those are only true in the unit circle. Using the unit circle, we got that sine squared plus cosine squared equals 1, which is the radius of the unit circle. So that's where that came from. Then we got some derivations of that by dividing both sides, by dividing everything by sine squared, dividing everything by cosine squared, and getting some other versions. So those were some identities, and those were, rather than verifying them, we created those ones essentially. And so now I want to talk about how to verify an identity. And this is a very big concept in trig. And this is a process. This is really where taking those wrong paths is something that's going to happen. You got to just accept it and deal with it and move on. So ultimately what verifying an identity is it's taking one side of an equation, using other identities or properties of these trig functions to manipulate them, then using some basic algebra skills. And when I say basic, I mean, just kind of your standard algebra skills to convert them so that they look like the other side of the equation. And it looks very similar to what would look like in this example here, where we're just simplifying, or we're just trying to write this as the product of two trigonometric functions. And so, like most things, the first step to do is try to get it into terms of sines and cosines. That's typically a very nice, easy way that we can get to work with these things. And so let's rewrite these as sine and cosine, because at this point, there's no way to write this as the product of two trig functions. So if we look at this, we have secant squared t plus cosecant squared t. Well, I know that secant squared t is just 1 over cosine squared t, and cosecant squared t is 1 over sine squared t. So now we're looking at these, and I'm like, okay, well, I need to get these as the product of two things. Well, I have the sum of two fractions. Let's add these fractions together to get at least one sum, because then at least it's one term, and we can look at trying to get it as a product once we see what we have. But let's get rid of this addition by adding this together. And to do that, we need a common denominator. So I'm going to multiply this left side by sine squared t over sine squared t, and this right side by cosine squared t over cosine squared t. And now when we do that, what we end up with is, here, there we go. We end up with sine squared t over sine squared t cosine squared t plus cosine squared t over sine squared t cosine squared t. And now we have a common denominator, and now we can add these fractions. When we add fractions, remember, once we have that common denominator, we just simply add the numerators together. So in this case, we end up with sine squared t plus cosine squared t all over sine squared t cosine squared t. Now, hoping that all of you guys are looking at this going, ooh, I see something we can do. And that's awesome. That's exactly right. So if we look at the numerator here, I see I have sine squared t plus cosine squared t. But we literally just talked about an identity involving those two. And when we add those two together, we get 1. So what's really cool is that means this guy here is really just 1 over sine squared t cosine squared t. Now, what's cool with this product, we know when we multiply fractions, we literally just multiply the tops and the bottoms together, right? So I can actually split this fraction, this singular fraction, to be 1 over sine squared t times 1 over cosine squared t. And The reason why is because 1 times 1 is 1. Sine squared t times cosine squared t is sine squared times cosine squared t. So the reason why that's nice is we're almost done. We're not quite done, right? Because we want to write this as the product of two trigonometric functions, not two fractions involving trigonometric functions. But what is 1 over sine squared t equal to? That is just cosecant squared t. And 1 over cosine squared t is just secant squared t. So we have now written this as the product of two trigonometric functions. And what's crazy here is that if we look at what we started with and what we ended with, what we started with is secant squared t plus cosecant squared t. And through doing these just basic algebra steps and applying definitions of trig functions and some of those things that we already know, we have that is equal to cosecant squared t times secant squared t. So what's crazy is we are saying that if you add secant squared and cosecant squared of the same angle, that's the same as multiplying cosecant squared and secant squared of the same angle. That's cool. Now this right here is an identity. And so a problem I could give you would be something like, here's this, I could say, here's this, and I would say something like, verify this identity, okay? And so what that would mean is you would just have to do exactly what we did. You start with one side of the equal sign, and you manipulate it using algebra and trig properties and definitions of functions like we did until you get to the other side. And so that's exactly what we've done. We just didn't have that right-hand side to begin with, okay? Now, a couple things that are important to be able to do when we are verifying these trig functions is factoring. Now, factoring may seem like something that you're like, well, it's not that important. We don't really need to worry about it, but it is. And it is something that will be very useful to do with these trig functions. So what I want you guys to do is I want you to pause this video and try to factor these out and see what you can get, okay? Now, this may be something that you are kind of bored with and don't want to deal with, and that's fine, except you're going to have to do these things later on in this chapter as well as in future things, maybe even say your next test. So pause the video, try to factor A and B here, try to factor those out into the product of two binomials. So in other words, two-termed expressions. All right, pause. Did you pause? All right. So welcome back. Thank you for doing this. That was very helpful. It means that you are practicing and engaging with the material, which is important. Now, let's look at how we factor these. There's a couple ideas that you can kind of use to help you out. And one is to simply replace whatever trig function we're dealing with just a random variable. So one thing you could do is instead of trying to factor 16 minus tangent squared of theta, you could say, well, let's let tangent of theta equal x, in which case then I end up with the expression 16 minus x squared. And I just have to factor that. And now that may be something that's a little simpler for you to deal with. And that is a perfectly great strategy. If that is something that makes this make a lot more sense to you, makes it work a lot easier to you, I highly recommend doing that. And I'm going to kind of simultaneously do both. But ultimately, when I'm looking at this part A here, I see I have 16 and I go, hey, 16 is a perfect square, right? And I know that because I do a lot of math work as a math teacher. It's weird that I do a lot of math. And you may not be necessarily as comfortable with that, but I'm hoping that at least the first few perfect squares you kind of know, right? And a perfect square is just anything that when you take the square root, you get an integer value. So things like 4, 9, 16, 25, 36, 49, 64, 81, 100, right? Those are the first 10 perfect squares. And the way I get those is very simply by taking 2 and squaring it to give me 4. 3 squared is 9, 4 squared is 16, and so forth. So once I see that these are perfect squares, right, because the other side is tangent squared, and I see that we're taking the difference, this is a really easy thing to factor. Let's go back up. To factor a difference of squares, we take the kind of square root of both pieces, the piece that would have been squared to get us there, and we add them and we subtract them, and that gives us what we want. And so if you think about multiplying this out, okay, we would do 4 times 4 would give us 16. 4 times positive tangent theta would give us 4 tan theta. The negative tan theta times 4 would give us negative 4 tan theta. And so when I have positive 4 tan theta and a negative 4 tan theta being added together, they cancel each other out and those pieces are gone. And then we end up with negative tangent theta times positive tangent theta gives us that negative tangent squared theta. And so that is how that works. If you're curious more about the difference of squares, feel free to go look that up, look up a separate video. There's a lot out there. That's something that you should be able to recognize the difference of squares and very quickly factor those out. Okay. Now this next one is a little more challenging, both in the trig basis, but also just algebraically. So I'm going to do this one algebraically. And what I mean by that is I'm going to replace cosine with a random variable. So if I just say that, let's let cosine t equal x, then what I get is I get 3x squared minus 13x minus 10. Now, it would be lovely if all of these were divisible by 3 and I could just pull that 3 out and then have a nice simple thing to factor. It's always easier to factor if the coefficient of our x squared piece is a 1. But unfortunately, that's not always the case. And so what we have to kind of think about here, is what we're trying to get. And so when I'm looking at creating these two things, I know that when I multiply the first two pieces together, I need to get a 3x squared. I need to get a 3x squared. The only way to multiply two numbers together and get 3x squared is one of them being an x and one of them being a 3x. Okay, it doesn't really matter which one you're using. Kind of if you put 3x here and an x here, or if you flip those, it doesn't matter. It's multiplication. The order doesn't matter. Okay. Now, the next parts here and here, when they multiply together, we need to get negative 10. Now, that gives us a few possibilities. We could have 1 and negative 10. We could have 2 and negative 5. We'd have negative 5 and 2. We have negative 1 and 10. Now you may be asking why I'm listing these twice, right? You're like, well, I have 1 and 10 twice, but notice the negatives are on different values, so they give us different kind of pairings. Now, if we didn't have this 3 here, we would just simply be able to be like, cool, which one of them adds to be the negative 13 that we're looking for? But because we have that 3, we have to be careful about how this works. So what ends up happening here is this 3 is going to, the 3x is going to multiply by this piece here. And then this piece here is only going to be multiplied by an x. So what I have to kind of figure out is, okay, if I multiply one of these by 3, and then I don't multiply the other one by 3, and I add them together, I need to get negative 13. Okay? So from these pairs, I'm going to get two different sets. And I'm going to do it like so. Here I'll multiply the 1 by, so basically I'll multiply the left side by 3 in this column, and I'll multiply the right side by 3 in this column. So this will be left, right. And what I mean by that is like this is our left and this is our right. So if I multiply the left by 3, which then what that would do is I would put our 1 right here and our negative 10 over here. I would end up with 3 minus 10. If I multiply the right side by 3 and the left side by 1, I would get 1 minus 30. If I do this all the way through, right, so left side by 3, get 6 minus 5. Right side by 3, I'd get 2 minus 15. Here I would get negative 15. Wait. I just noticed an error. Those are the negatives. This is what's downside to not being in class. So here from the left side, I'd get 15 and negative 6. Or over here, I would get, oh, that's not right again. Negative 2, 5, and negative 6. Down here, I would get one. Okay. 10. There you go. Okay, our table looks better now. I apologize about that. Mental mistake on my part. Table's fixed. Right, we have 1, 2, 5, 10, positives, negatives. Okay, so then here we would get 30 and minus 1. And over here we'd have 10 and minus 3. Okay, now that I've gotten all these right. So now these are all the possibilities of what we have. And so notice these are all kind of originating from these four sets right here. Okay, these 4 sets. So I need to look, of these 8 combinations, which one gives me a sum of negative 13? And I can see that's this guy right here. So that came when I had a factor of 2, a positive 2, and a negative 5. And the negative 5 was multiplied by the 3. So that means I am going to have a plus 2 here and a minus 5 here. Because I need that negative 5 to be multiplied by that 3. Okay, so that's a whole lot of work for this one little problem. And I totally understand that. This is not something I typically do a whole lot of, especially I would never do a problem like this on a test. Just because I don't want to waste this much time with you guys factoring. That's a 111 skill. You should already have this, so I'm not going to test you on your ability to factor these, things like that. But it is a good practice and a good refresher. That's why I went through and kind of went on a detailed explanation of how to do that. It really kind of comes down to quite a bit of guess and check. And that's why you're really hoping you don't have things like 24 that have a lot of different factors. And so we just want to kind of be careful with that. So I've now factored this to be 3x plus 2 times x minus 5. But the problem is I'm not done. And the reason I'm not done is because notice in the original problem, there's no x's. So I need to now substitute cosine of t for all of my x's. So what I end up with is 3 cosine t plus 2 times cosine t minus 5. And that's how that works. So I hope that this is making some sense to you and that you are able to kind of make some progress in your understanding of factoring if you weren't already very clear in that. But let's move on. So let's talk about what does it mean to verify an identity. Now I know this is a big wordy part and you're going to expect me to just read this to you, and I'm gonna, but I also want to kind of expand on these ideas and make sure you guys are really focusing on this. Don't get to example 3 just yet. So to verify an identity is to show that it is true for all values of the variable. The verify an identity is to give proof that it is true. So when you're trying to verify an identity, what you're trying to show is that no matter what value of theta you put in there, as long as it is defined, in other words, as long as that cosine or sine is defined for whatever you put in there, so you can't put in like square, you have to put in something that it actually works, that identity will always be true. So if you think about something like x plus 2 equals 3. This is not an identity. This is not always true. This is only true when x equals 1. So that isn't something that you could just show to be true all the time. Okay. Now, so for identities, you want to start with one side of the equation and using a sequence of equivalent expressions, so using ideas of trig definitions, things like sine or like cosecant is 1 over sine, tangent is sine over cosine, things like that, to get from one side to the next. Okay. Now, what side you start with is really not a super obvious thing. You have to kind of figure out what side is the most beneficial to work with. That's not something you're just going to know. Let that sink in. You're not going to always be able to look at an identity and know exactly which side you want to work with, the left side of the equal sign or the right side. Most of the time, you want to work with a side that has kind of the most algebra going on and the most arithmetic. And so if we're looking at, say, jumping to example 3a, I look at those two sides and I see one side is the product of two things, and the other side I have the difference of two squared things. And so I am looking at that side, and that's the side I want to work with. So how can I show that tangent of theta times sine of theta squared is equal to tangent squared theta minus sine squared theta? Okay. Again, like I said, so one of the things that I will typically do, and this is just kind of for me to keep organized in what I'm doing, is I will say what side I start with. So I want to start with this right-hand side here because, like I said, it's got the subtraction. I know I can convert these things into fractions and then combine them together and see what things cancel and simplify and kind of go from there. That's kind of usually a very common thing. So I'm going to start with the right-hand side, and first thing I'm going to do is I'm going to convert into fractions. And so I'm going to change tangent squared theta to be sine squared theta over cosine squared theta minus sine squared theta over 1. Now, to be able to combine these fractions, I'm going to multiply the term on the right by cosine squared theta over cosine squared theta. Okay. And so once I do that, the denominators are both cosine squared, so I end up with sine squared minus sine squared theta cosine squared theta all over cosine squared theta. Okay. So now looking at this, trying to identify what it is we need to do, we kind of need to look at what we have. So in the denominator, I just have cosine squared. That's really not going to help me out. In the numerator, I have sine squared theta and I have minus sine squared theta cosine squared theta. I don't have Pythagorean identity, right? So that's not a setup that I have right now. But I do have sine squared theta in both of the two terms in the numerator. So let me factor that out. So in the numerator, I get sine squared theta times 1 minus cosine squared theta. That's all over, cosine squared theta. Now, looking at this, we're like, okay, cool. How am I going to get to this being tangent theta sine theta squared? Well, right now I can see if I look at just these left pieces, the sine squared theta, and the cosine squared theta, that's my tangent. So how am I going to get 1 minus cosine squared theta to be sine? Wait, the Pythagorean theorem, the Pythagorean identity, right? Let's go back up to that. Remember, I can isolate any of these I want. And I know that sine squared theta is equal to 1 minus cosine squared theta. So what I can do is in this parentheses here, this 1 minus cosine squared theta, that is sine squared theta. So this becomes sine squared theta times sine squared theta divided by cosine squared theta. We're almost there. Now, you may be wondering why I didn't combine those signs to say sine to the fourth theta. But the reason I didn't is because I don't want it to look at, I don't want to just simplify this. What I want is I want to get to this left-hand side here. Okay, I want it to look like tangent theta sine theta squared. So when I'm looking at what I've got, I can see it now. Because when I have a product over a single thing like this, I can take this cosine squared theta and put it underneath either one of these two things. It doesn't go into both. It only goes into both if I had addition or subtraction in that numerator, such as I did back here. So what I can do is I can split this product to be sine squared theta divided by cosine squared theta times sine squared theta. And we know sine squared theta over cosine squared theta is tangent squared theta. Now, we're not done yet. And the reason we're not done yet is because of the way the left-hand side is typed up. The left-hand side is typed up tan theta sine theta squared. But we know, to refresh ourselves, that a times b squared is just, whoops. Sorry about that. A times b squared is just a squared times b squared. And so that means because this is a product of two trig functions, I can pull this exponent out front or outside of it, giving me tangent of theta times sine of theta squared, and that is equal to the left-hand side. And so that is the process of verifying this identity. So we have just verified this identity. Yay! Now, let's scroll down. Let's do this again. Now, every time it's going to be different because every identity is different, right? It's not going to be the same exact steps and processes every time. So what I want to look at here is I want to look at what has the most to do. Look at this right-hand side. I have 1 minus sine theta. There's really nothing I can do with that, right? There's no squares. There's nothing like that. So I'm not going to use that. I'm going to start this time with the left-hand side. Okay, so I have cosine squared theta over 1 plus sine theta. Now, the only thing I can really do here is deal with this cosine squared theta. And what's cool is very similar to how up here, how I took this 1 minus cosine squared theta and turned that into sine squared. I can take cosine squared and I can change that to be 1 minus sine squared theta. All right. Now, you're like, cool, I have the 1 minus sine, but this time it's squared, and I still have this in the denominator. We're making progress, but we're not quite there. But because I have that sine squared, right, don't be like, oh, well, that's just 1 minus cosine, because then you get 1 minus 1, and that just becomes cosine squared, and you just back up at the left-hand side. But this is a difference of squares, because what's 1 times 1? It's just 1. So that means I can factor this numerator. When I do, I get 1 plus sine theta times 1 minus sine theta. That's all over 1 plus sine theta. Ooh. Those cancel out. And once those are canceled, I am left with 1 minus sine theta, which is exactly the right-hand side. So that's it, right? Now you may be going like, yeah, cool, that's it. That was not great or confusing or anything like that. What we have to think about here is as I'm going through the examples, I'm showing you some of the common tools, some of the common techniques that are going to be applied to be verifying Turing identities. In this first one here, right, we combined the fraction, we created fractions and added them together, right, using the Pythagorean identity, right? Factoring is a huge piece, right? That's why we did this example up here with factoring, because you are going to have to factor. And if you're terrified about that, better get over it, okay? Plus, well, right now when I'm doing this video is October, so that's spooky season, so it's okay if you're a little terrified of things. So, in example B, we used the Pythagorean identity to change the cosine squared. Then we used factoring, in particular the difference of squares, and then we canceled them things out. So those are all things that are very common in doing trigonometric verification of identities. Okay, factoring, adding fractions, canceling things out, using previous identities that we've already done. You cannot use an identity that you are proving to prove an identity. Okay. So in other words, you can't say that 3 plus 3 equals 6 because 3 plus 3 equals 6, right? So you can't use what you're trying to show what you're trying to show. So let's move on and do another example. Hopefully this side is very obvious which side we want to be doing the work on, right? That right-hand side, we have 2 cosecant theta. There's no way I'm going to be messing with that and trying to make it look like this left-hand side that's all this crazy mess. I definitely want to work with this left-hand side, and I see that I have addition, so I just want to, first thing, I want to add these 2 fractions together, okay? So to do that, I start with the left-hand side, and I'm going to give myself some room. I need to multiply the left piece by sine theta over sine theta. That's multiplying our sine theta over 1 plus cosine theta plus cosine theta over sine theta. And this time I'm going to multiply this guy by 1 plus cosine theta over 1 plus cosine theta. And what I end up with here is sine squared theta plus now let's do a little side work here. Okay. I'm going to look at the 1 plus cosine theta times 1 plus cosine theta. So 1 plus cosine theta times 1 plus cosine theta. I just don't want to do 50 different steps. I don't have a lot of room. So I want to kind of simplify this process a little bit. Multiply these together, I get 1 plus cosine theta plus cosine theta plus cosine squared theta, which just leaves us 1 plus 2 cosine theta plus cosine squared theta. So I can add that in here. So 1 plus 2 cosine theta plus cosine squared theta. And that's all over 1 plus cosine theta times sine theta. Okay. If I look at this guy here and this guy here, I have sine squared theta plus cosine squared theta. That equals 1. Squeeze it in here. So I end up with 1 plus 2 cosine theta over 1 plus cosine theta sine theta. Now the 1 plus 1 obviously gives me 2, so I have 2 plus 2 cosine theta over 1 plus cosine theta sine theta. So we got this one here when we multiplied the 1 plus cosine theta times 1 plus cosine theta, and we're getting this one here from the sine squared theta plus cosine squared theta using the Pythagorean identity. Now I have 2 plus 2 cosine theta. Both of those have a 2 in it, so I can pull that out. And if I do that, I get 2 times 1 plus cosine theta over 1 plus cosine theta sine theta. And those cancel out, leaving me with 2 over sine theta, which is just 2 cosecant theta, which is our right-hand side. Now, you do not have to do this whole LHS equals and start there. Then when you finish, go equals RHS. That's just something, again, I do just to kind of signify where I started with the left-hand side, and now I'm done because I've gotten the right-hand side. Okay. Again, not something you have to do, just something I do. All right. That one was a little messier, but we're okay. We can do it. Now, this is a less common trick, but it's still a trick that we like to be able to use. So I'm going to start with the left-hand side, giving me cosine of t over 1 minus sine of t. And what I'm going to do is I'm going to multiply this by 1. No, I don't need that shape. And so as you can see, I just multiply by 1. But what this does for me, okay, my numerator, I end up with cosine of t times 1 plus sine of t. So what that does for me, which is really nice, is, ooh, look, that is the numerator of the right-hand side that I want. It's that 1 plus sine of t. Now what happens if I 1 minus sine of t times 1 plus sine of t? That's the difference of squares. That's different. That's what that factors to. So that means when those multiply together, it's 1 squared minus sine squared t. And just because I don't want to have to write another step, 1 squared is just 1. Awesome. So now what? I have what I need over here. Well, what does that denominator look like? The denominator is 1 minus sine squared t, which that's cosine squared t, because that's the Pythagorean identity. So I end up with cosine t times 1 plus sine t over cosine squared t. Now I can cancel out this cosine and this squared. So this cosine t in the numerator cancels out with one of the cosine t's on the denominator, because cosine squared t is just cosine t times cosine t. And so what I'm left with is, in the numerator, 1 plus sine t, and in the denominator, I have cosine t. And that is our right-hand side. So here the trick was to multiply by 1 plus sine t for a couple reasons. One, it gave us what we needed in the numerator. And also it helped us to simplify out the denominator. So this is always something that when you have something kind of similar like this, that's a good idea to kind of multiply this together. Now, if you look at what we've got going on here, I can see in the denominator on the left-hand side that 1 minus sine t, and the numerator on the right-hand side, 1 plus sine t. I can see those are the factors of difference of squares. So that is another sign to me that I'm just like, okay, I want to do this kind of weird multiplication thing. This is a trick that is not used in a lot of other areas. So it is kind of maybe a newer trick. But make sure you guys are kind of aware of it, right? If you want to write down a separate list with kind of the tricks to use in verifying things, put this on there, multiply, however you want to word it, whatever makes sense to you. But this is definitely a useful trick to do. So let's look down here, part E. It seems like it's going to be really scary and big, but it's really not too bad. So I have cosecant theta plus cotangent theta over cosecant theta minus cotangent theta. Well, let's just start by getting these written in sines and cosines. And what's telling me I want to do that, first of all, is I have cosecant and cotangent, and those are not things that I deal with a lot. Sines and cosines are more comfortable. But also, if I look at the right-hand side, I have cosines over there, so I'm going to need to get to cosine eventually. So let's just start. Let's just start by doing that right off the bat. So we'll take our left-hand side. And so cosecant... So cosecant is 1 over sine theta, plus then cotangent is cosine theta over sine theta. And all of that, cosecant theta, that's just 1 over sine theta minus cotangent theta is just cosine theta over sine theta. Okay. Now, look at both of the numerator and denominator. We can see that they have the exact same denominators in their own fractions, right? We have 1 over sine theta plus cosine over sine theta, right? So I can just add these. So when I add the numerators together, the fraction of the numerator, I get 1 plus cosine theta over sine theta. And then that is all going to be over 1 minus cosine theta over sine theta. And what happens when you have a fraction divided by a fraction? Right. We multiply by the reciprocal. So 1 plus cosine theta over sine theta is still the same, but now we take the reciprocal of that fraction in the denominator. So we end up with sine theta over 1 minus cosine theta. And sine thetas cancel. I get 1 plus cosine theta over 1 minus cosine theta, and that is our right-hand side. Thought a nice easy one might be a little more fun right now, right? So notice what we did there, right? We used that technique again of converting things from cosecants, cotangents, secants, tangents, and all those other functions, just converting them into sines and cosines. It typically will reduce the number of trigonometric functions, plus it utilizes some simpler identities. Like we know that there is a trig identity involving cotangent and cosecants and secants and tangents. But my guess is you don't remember those off the top of your head. But my guess is you probably already remember sine squared plus cosine squared equals 1. And so that's an easier Pythagorean identity to work with. And going from that to its alternate forms of sine squared theta equals 1 minus cosine squared theta and cosine squared theta equals 1 minus sine squared theta is a much easier conversion. And so by converting things from these other 4 trig functions into sines and cosines is a nice, useful tool, especially when in this case we can see the side that we're going to has cosine in it, so we need to have it in that direction. Now, let's move on. We are almost done-ish. We have 4 more identities that I want to verify. And the reason I want to do this is just because we need the practice. I lied, 5 more. So, I have sine of alpha times tangent of alpha equals tangent squared alpha divided by secant alpha. Now again, looking at this, which side do we start with, right? I can do some stuff on the left-hand side. Sine alpha is tangent of alpha, or times tangent of alpha, I can convert that tangent into sine over cosine, multiply, get sine squared over cosine, and I could make some progress. I could make some things maybe work, and maybe I'll get to where I need to be. But I don't really know if I'm going to be able to do that. So instead, I'm going to focus on the right-hand side using tangent squared alpha times secant alpha. Okay, and so the right-hand side here gives me tangent squared alpha over, and instead of secant, I'm going to make my first move here. That's tangent. Secant is 1 over cosine alpha. And as we just stated, if we divide by a fraction, that's multiplying by the reciprocal. So I get tangent squared alpha times cosine alpha. Now what? Well, let's just simply convert tangent squared into what we know it is. And that is sine squared alpha over cosine squared alpha. Cosine alpha. Cool. So what happens? Well, that squared goes away and that cosine goes away, leaving me with sine squared alpha over cosine alpha. Okay. What is sine squared alpha? Well, that's just sine alpha times sine alpha over cosine of alpha. I can divide those whichever way I want, so I'm going to do sine of alpha times sine of alpha over cosine of alpha, and that is just equal to sine alpha tangent of alpha, which is our left-hand side. Whew. Now, you may be thinking, hey, that was like very similar to what we were talking about doing with that left-hand side, right? Converting tangent to sine over cosine, and then we'd multiply, we'd get sine squared over cosine, and you're like, hey, look, if we kind of backtrack from our left-hand side, that's where we had right here. But if you look at what we did to get there, right, it wouldn't be a very intuitive step to go from sine squared alpha over cosine alpha, be like, I want to multiply this by cosine alpha over cosine alpha. That's not a very intuitive step. And you may be like, well, how is it an intuitive step to multiply by 1 plus? It really wasn't. And it's something that you're going to have to practice with. But you notice going the way we went, there's no intuition that we needed to do. We just converted to our sines and cosines, canceled, and split. So again, try to always work with the side that has more going on. So here the right-hand side had a squared piece and had a fraction. So there's more I can do with that. So cosine squared theta minus sine squared theta is equal to 1 minus 2 sine squared theta. All right. What can we do? Well, this is a really easy one. And what this really relies on is, so I'm going to start with our left-hand side. Perhaps, if it'll let me. Start with our left-hand side, thank you. And I know I want to end up with everything in terms of sine. So let's change cosine squared into sine squared. And to do that, we use that as just 1 minus sine squared theta. Then we have minus sine squared theta. Combine like terms. And we're done. That's it. Sometimes it's that easy, right? All we did was we used the Pythagorean identity to convert cosine squared theta into its 1 minus sine squared theta piece. And then combine like terms. Sometimes these are really that simple. All right. We're getting there. We're making our progress. Cosine t minus sine t is equal to sine squared of negative t minus cosine squared of negative t, all divided by sine of negative t minus cosine of negative t. I bet you can figure out which side we should start with, right? We always want to start with the side we can do more with. Now, before we do that, I want to do a little exercise with you. So if I have sine squared of negative t, written like this, it's not very obvious, But one thing that I can do is I can rewrite this so it's sine of negative t squared. Now, if you remember, we had those kind of negative angle identities that we talked about in 7.1, and sine is an odd degree or an odd symmetry function. So sine of negative t is negative sine of t. And if I'm squaring negative sine of t, well, if we square negative, it's just the positive. And so that just becomes sine squared t. Okay. So let's use that. So starting with our right-hand side, okay, I'm going to make these conversions first. So sine squared of negative t, as we just saw, is really just sine squared t. Then minus, so cosine squared of negative t. Since cosine is a even symmetry function, cosine of negative t is just cosine of t. So it's just cosine squared of negative t over negative sine of t minus cosine t. So what we did here is we just used our negative identities to work with that. And now if we look at the numerator, what do I have in the numerator? Well, I have the... Are you going to say it? Oh, I know I can't hear you. It's just keeping my teacherness in me, right? It's a difference of squares. Very clear. Sine squared minus cosine squared. Let's do it. So then that factors to be sine t plus cosine t times sine t minus cosine t, all over negative sine t minus cosine t. Now you may be asking yourself, well, how in the world does this help me? Right? I'm subtracting the cosine t, and in the numerator I have a minus, so cosine t on the right, but it's a positive sign and it's a negative sign. Well, what if I took out that negative? Not take it away, but took it out. So I have negative 1 times, now it's a positive sine t, but it's also positive cosine t. Ooh, that takes those out. So I'm left with sine t minus cosine t over negative 1, which is negative sine t plus cosine t. Now you may be like, how does that get me to the left? But really, we can see it's just a rearrangement of these two terms. And so the cosine t, we just move forward. And then we can flip subtraction, right? We just have to remember, then we don't think of it as subtraction as much as the negative is attached to that piece. So it's cosine t minus sine t, and that is our left side. All right. So we are getting there. This one right here. Skip. Because I like you guys. Again, this is just using some identities, using kind of involving this relationship here. Tangent of pi minus 2, or pi over 2 minus theta. That's just cotangent of theta. And that's just to deal with the relationship of those in that kind of unit circle. Not something I'm too worried about. We're going to move on. So let's look at J. This one is going to be very weird and very different. But we're going to do it because it's fun. So what we're going to start off with is kind of defining, we're going to let theta equal the inverse tangent of v. So that means that tangent of theta is the tangent of the inverse tangent of v, which means that tangent of theta is v. Okay. Okay. So if tangent of theta is v, what do we have a triangle here? Here's theta. So tangent is opposite over adjacent. So v, what if I say this is v over 1? Ooh, that does something. Okay, okay. So, so we've got v, we've got 1. I need the hypotenuse. Well, that's just Pythagorean theorem, right? That's just a squared plus b squared equals c squared. So that means this equals 1 plus v squared. Square root of 1 plus v squared. Yeah, if you're confused on that, right, feel free to work that out yourself on your side. 1 squared plus v squared equals c squared, square root both sides. This radius can't be negative, so it's the positive square root of 1 squared, which is 1 plus v squared. So now let's look at the left-hand side. Sine of inverse tangent of v is equal to, that's just sine of theta, right? Because inverse tangent of v is theta. And if we look at our triangle we created, theta, sine of theta is v over the square root of 1 plus v squared. Hey, there we have it. That was a super unique one, very different, mainly because it involves the inverse tangent. It's something I wanted to show you guys. I'm not really going to do any problems with that. It's kind of a cool, fun thing to do, kind of fun thing to look at. So that is the end of this lecture. Big takeaways. I know these problems. I've written, I designed this, and I've done a lot of these, so I can look at a problem and I have a pretty good sense of where to go. When I first took 112, I did not have a good sense of where to go. And most likely you're not going to have a great sense of where to go. You may, and that's awesome. So keep in mind that if you are doing these proofs and you are these verifications of identities and you're struggling to figure out, you keep doing things and it gets a little way and then you don't know what to do, that's okay, right? But go back through and make a list of what techniques and tools we used, right? Things like getting things written in terms of sine and cosine, factoring things, right? Whether it's factoring things out or factoring out, terms like difference of squares and stuff like that. Canceling things out was really useful. Using the Pythagorean identity is a very helpful thing here, right? Go back through and list off some of those different things that we have done. Yeah, I just think you guys are ready to go. I think you guys can hit it now. So with that, I will see you guys next time for 7.3.